Hi, hello. So of course, last time we started a new chapter, so very exciting, starting something brand new. And the very first thing that we saw, isomorphisms, is something that is usually, for folks in this class, is usually something they've never seen really too much like it before. So we went through a couple of examples. You have to start off with easier examples. So for the check-in, what I want to do is do an example that's just a little harder, just that sort of that notch, sort of more technically complicated. Same ideas, but more technically complicated. Okay, so let's get to it. So we have the space R2, the regular plane, and the space P1, which is the linear polynomials, and I want to show that they're isomorphic, not using the sort of obvious isomorphism that the first component maps to the constant term and the second component maps to the coefficient of x, but instead using a little different isomorphism, and so that makes it kind of more technically difficult, and so that illustrates what it is that we want to illustrate for the check-in. Okay, so let me bring that down and start working. We saw last time the how-to, 4 different steps that a person needs to show. Person needs to show one-to-one, onto, and preservation of addition and preservation of scalar multiplication. So I'll just start in. I better remind myself how it goes. Let's see. It is AB is associated with, and it's A minus B plus A plus B x. And now, perfectly sensible, perfectly reasonable for a person to say, what is happening here? And the answer to an abstraction, if you're saying, I'm not getting what this formula is trying to tell me, the answer to an abstraction is always the same, is to concretize, that's a word, it is to try it with some numbers. So I'm going to put in some numbers, 1, 5, and 1, 5 is associated with negative 4 plus 6x. So 2, 2 is associated with 0 plus 4x. Okay. So all that's happening here is I'm mapping 2 tall vectors. I'm associating 2 tall inputs with linear polynomial outputs, and it's a somewhat peculiar or at least a little bit not unexpected association. But okay, fine. Okay, so let's start off. We got to show that it's one-to-one. And the how-to says, here's how you show it's one-to-one. You assume that F maps a first one to a second one. A1, B1. I think I got that right. There's the matching parens. And A2, B2. And again, I think I got that right. A lot of parens, but I think I got it right. And then when I finish, I have to show that A1, B1 equals A2, B2. So my goal is to get from here to here. Okay, so let's see here. F of A1, B1 is what? A1 minus B1 plus A1 plus B1 x, that's this part here, and then this part here is A2 minus B2 plus A2 plus B2 x. Okay, so again, I'm trying to get from here to here. For this, I just wrote in what it equals, that's all. So how am I going to get this? In order to get this, I need, working backwards, I would need this. What? To get that then I would need A1 equals A2 and B1 equals B2 is what I would need. What I would need to get that. So let's see. So I have here 2 linear polynomials, and I got to conclude this. So it seems to me I have to conclude that A1 equals A2 and B1 equals B2 by looking at the constant terms. So from we have A1 minus B1 equals A2 minus B2. And A1 plus B1 equals A2 plus B2. Okay? And how do I get from there to there? Well, I guess there's a variety of things that a person could do. A person could set up some linear systems, but personally, I would simply add. I would take the left-hand sides, a1 minus b1 and a1 plus b1, and add them to get 2a1, and I would take the right-hand sides, a2 minus b2 and a2 plus b2, and add them to get 2a2. So adding gives 2a1 equals 2a2. And can you see that subtracting will give? I'm sorry about my handwriting. Gives, so a1 minus a1 goes away, negative b1 minus b1, so minus 2b1 equals minus 2b2. So I got, and I even had the exact right amount of space, which hardly ever happens. Okay. So one-to-one was a question of writing down where you start from, writing down where you have to end, and figuring out how to make the two meet in the middle. And of course, it can be the case for an individual problem. And you say, I just don't get it. I just didn't see how to make them meet in the middle. But there must be a way to make them meet in the middle. Okay? Onto is a little trickier, so we'll try a fresh piece of paper. So for 2, onto. So for onto, what I find is that what does me the most good is to try it first concretely with with numbers, and then right away I'll start saying, okay, so the pattern is. So I'm going to ask myself, if I pick kind of some numbers, I'm going to ask myself f of what makes, how about 3 plus 4x? I didn't pick 3 and 4 for any good reason. I just made up two numbers. In fact, if you make up, if you don't pick sort of 0 and 1, if you try to pick up kind of crazy numbers, that is often more helpful than picking sort of special numbers. Okay, so I need that a minus b equals 3. So I'm looking at f of ab equals 3 plus 4x, and I'm asking what are a and b. So of course I need that. You remember that ab maps to a minus b, a plus bx. So I need that a minus b is 3, and a plus b is equal to 4. Well, this is familiar territory. Off I go on Gauss's method. Minus rho 1 plus rho 2 gives me a minus b equals 3, and what minus 2b equals 1, minus 2b equals 1, minus 2b equals 1, and so b is 1/2, and a minus 1/2 is equal to 3, so a is 7/2. Okay, so the key idea there, once I boiled it down to some numbers, the key idea there was that I got an equation where a and b are the unknowns, and the given things, the 3 and the 4, are the constants on the other side. So if I want to figure out f of what equals p plus qx, then I get a linear system. A minus b equals p, and a plus b equals q. Gauss's method, I'm just aping what I did with numbers, only with letters. Gauss's method minus rho 1 plus rho 2 takes you to a minus b equals p, and 2b, oh, this is a plus 2b. That's right, I copied it down wrong, I apologize. So 2b equals, what is this now, minus p plus q? Minus p plus q. And so I conclude that b is equal to, b equals minus p plus q over 2. And from that I get a minus p plus q over 2 equals p. And so what a is, change the sign, a is p over 2 plus q over 2. A is p over 2 plus q over 2. Okay, so given a p and a q, I can tell you what a and b are. Now I'm ready for onto. So here's the argument for onto. So consider P plus QX in the outputs. Observe that we have that f of P over 2 plus Q over 2 and B is minus P over 2 plus Q over 2. I got the parentheses all wrong. There we go. So that's P over 2 plus Q over 2 minus P over 2 plus positive Q over 2 is equal to P plus QX. And that's easy to verify. Maybe I shouldn't have just written this. Maybe I should have written something like this. Is equal to P over 2 plus Q over 2 minus negative P over 2 plus Q over 2 plus A plus B. P over 2 plus Q over 2 plus negative P over 2 plus Q over 2 X. Sorry about the handwriting. And when all the smoke clears, the P over 2's add to P, that minus minus makes plus, P over 2 adds to make a P, and the P over 2 and the minus P over 2 cancel to make a Q. And so a lot of mess with the handwriting, but anyway, it turns out that I did a lot of work to figure out what's the right formula, but once I have the right formula, I just pull it out, verify that it works, and boom, you're done. So given a member of the output space, there is an appropriate member of the input space. It took me a little while to figure it out, and the key there, it always seems to me the key there, is to start off with numbers and then switch with letters. If you're scratching your head, what am I asked to do? Change it to numbers, and then it's so much easier to figure out what to do when you change it to numbers. Then at some point you say to yourself, I see the pattern, I'll change it to letters. Now you've got a formula. Verifying that the formula works is usually easy. Okay, that was on to. Fortunately, the other two parts are usually routine. So for 3, preservation of addition. There we go, a little sideways. Preservation of addition. For preservation of addition, it's usually just a question of seeing if you can make the beginning match the end. So I have f of A1, B1 plus A2, B2. And I've got to get, after some amount of work, maybe half a page's worth of work, I got to get f of A1, B1 plus f of A2, B2. Okay? And I do think when you first start these out, it helps to break it into 2 parts and work from the bottom up and the top down. But a person does get better after some point, so let's give it a get better whack. F of A1 plus A2, B1 plus B2. And what does F do? It takes the first minus the second, so that's A1 plus A2 minus B1 plus B2. That's the constant term. And then the coefficient of x is A1 plus A2 plus B1 plus B2. And the whole thing is multiplied by x. And then, right, it's pretty clear what I got to do. I got to bring the 1's and the 2's and separate them out. So I get equals A1 minus B1 plus A1 plus B1 x plus A2 minus B2 plus A2 plus B2 x. And then that line and that line are fine. I didn't leave the right amount of space, but I almost never do. Okay, and if you didn't see how to do that, you could certainly work from the bottom up and see that this is f of A1, B1 right there. This is f of A2, B2. This is what happens when you f the combined, and then you say to yourself, they're the same. Okay. And then for 4, preservation of scalar multiplication. So here, it's much the same thing. I write down here f of r times ab. I don't need the ones and the twos. They're not wrong, but I don't need them anymore. There's only one vector. And I got to somehow make that come down to r by f of ab. And again, if you get stuck, you can always work from the bottom up and the top down at the same time and see if they meet. I'm gonna do top to bottom because a person does get better at this over time. So this is f of RA RB, because that's how you scalar multiply vectors. And what does f do? It takes the first component minus the second, RA minus RB, and then the first component plus the second, RA plus RB. And I'm going to bring out all the, oops, I forgot the equal sign. I'm going to bring out all the r's, r times a minus b plus a plus bx. And that's right. Okay, so I made the two come out equal. And again, if you're having a little trouble with it, what's a good technique is to write down here r times f of ab, and that would give you this. F of RA RB would give you this, and you say, the two are the same. So we're good. Okay, so that one's a little trickier. In particular, the onto is the part that often gives a person trouble. And to me, the technique that works the most there is the technique of a technique that always works with abstraction. Anytime you have trouble with abstraction, see if you can make it concrete. If you can somehow turn it into numbers instead of letters, that seems to help a person, or often seems to help a person sort of make sense of it, put it together in their head. What part is what? Okay, so we're ready for talking about the second half of isomorphisms, and it's really sort of more of the same. So last time we introduced isomorphisms and we worked with them, a couple of relatively easy ones. In the check-in, we worked with a relatively hard one, so we feel like we have some practice now. We'll get a little more practice today and talk a little bit about what isomorphisms has to say. One way sometimes to help understand what something is to talk about examples of what it isn't. It's a silly example, but if you want to teach a 3-year-old what a cat is, you might show them also a couple dogs and say, not a cat. So what is it about preserved addition and preserved scalar multiplication that a person can learn? And it does seem to me one way to help understand that is to look at an example of a map that does not preserve. So here's a map that does not preserve. F of xy is the too tall vector x squared y squared. And it doesn't preserve, for example, 1, 0 and 2, 0 add to make 3, 0. F takes 3, 0 to 9, 0. However, f of 1, 0 and f of 2, 0 doesn't give 9, 0. F of 1, 0 is 1, 0, f of 2, 0 is 4, 0, doesn't give 9, 0. So it is not necessarily the case that all functions have this property of where you can break along the plus sign. That preservation of addition property doesn't hold for all functions. In fact, it rarely holds. So that preservation property is special. And special means that it will give us special results. Okay, so talking about isomorphisms, one kind of isomorphism that we'll talk about a number of times is isomorphism of a space with itself. An isomorphism of a space with itself is called an automorphism. So we're talking here about how spaces are related. We might want to relate a space to itself. So if we relate a space to itself, that's called an automorphism. Morphism means map, auto means self, so self-map. Just as an example, I'm going to take the plane, regular xy plane, and a dilation map multiplies all vectors by some non-zero scalar. In my drawing here, I multiplied them all by 1.5. I couldn't multiply them, it's too big because it fell off the top of the map. So I multiplied them all by 1.5. Okay, that's called a dilation map. And it's a perfectly good isomorphism. It's easy to check that it's an isomorphism. Go through the 4 steps and it's easy to check. Another automorphism is a rotation. So you can turn all of the vectors by the same angle. I'm rotating counterclockwise because that's traditional to rotate counterclockwise. Here by an angle of pi over 6 radians. Okay, so it's easy to check that that's an isomorphism. You might want to close your eyes and say to yourself, is it one-to-one? Is it onto? Does it preserve addition? Does it preserve multiplication? One more automorphism is a map that flips all the vectors over a line through the origin. So here I have a vector u and a line through the origin. That's the line at 45 degrees just because I thought it made it something easy to see. And when you reflect u over that line, you get f sub l of u, and that, again, that's an isomorphism. It's an isomorphism of the space with itself, checking that each of these three, the dilation, the rotation, and the flip, is an isomorphism, is pretty routine as one of the exercises. Well, a person might say, why are we studying automorphisms? I thought isomorphism meant just like, and it's obvious that the plane is just like itself, so isn't this entirely silly? So I want to go back and think about the rotations of the plane by theta radians counterclockwise. They say something. If you're saying that the plane is the same as itself after you rotate it 15 degrees, if you're saying that the plane is the same as itself, you're talking somehow about uniformity. You're describing the plane as being uniformly flat over the entire plane. So the part near the origin and the part that's near, x equals y equals whatever it is, those parts are the same. There's a flatness there. So with respect to rotation. So the fact that rotation gives you an automorphism has something to say about the structure of the space. These maps tell us things about the spaces that are being mapped. So the space in this case near the x-axis is just like the space near the y-axis, because you can rotate 90 degrees and turn the x-axis into a just like area, the y-axis. So these maps will tell us something about what the spaces are like. So one lesson is that we can use the map to describe relationships between spaces. If maps are isomorphic, then the relationship makes precise the intuition of just like, and in particular, if you talk about a space and itself, you can describe somehow a uniformity of the space. When I did dilation, I multiplied everybody by 1.5. The space is just like itself, further out. So in is the same as further out. Okay, and then the second lesson, also the lesson of the check-in, is that while there are obvious automorphisms, there are obvious functions from the space to itself that are isomorphisms. Nonetheless, there are non-obvious, non-trivial automorphisms of spaces, and that they have something to say. They tell us something about the space. They give us a description of the space as uniform with respect to some measure. Okay, so ending up with a couple of quick results about isomorphisms. First is that an isomorphism maps a zero vector to a zero vector, and this is just simply some straightforward algebra. So you fix some v in the vector space capital V, and remember that vector spaces are never empty, so there must be such a thing. Then f of the zero vector is f of 0 times v. Preservation of scalar multiplication means you bring the zero out. And 0 times f of v is 0 times is the zero vector in W. So that gives you that. Okay, one more result here for the day. So if you have a map between vector spaces, then these statements are equivalent. The two that we had in the definition of isomorphism, preserves addition and preserves scalar multiplication, is equivalent, says the same thing as, saying that f preserves linear combinations of the two. So you can take these two statements and combine them into one, and indeed sometimes it's more convenient when you're trying to check, for example, that something's an isomorphism, by checking one statement rather than by checking two. And you can do this with more than two vectors. You can do it with any finite number of vectors. Okay. And the book contains the details of both the proofs. They're not especially interesting, so I'm not going to go through them. They don't really have anything. You won't look at it and say, really, what's line 7 saying? All right, and then the remark down here says, if you look at the proofs, they only depend on the clause 2 of the definition about preservation. They don't depend on one-to-one and onto. So we'll say more about that in the next section. In the next section, section 2 of this chapter, we'll consider maps that aren't necessarily one-to-one and onto, but that do preserve. Okay, one last example. Here's a line through the origin with slope 2. y equals 2x. That's a vector space. If you parameterize it, it's all multiples of 1, 2. We've done this many times. What that suggests is that the line L is somehow just like R. There's a point on L associated with 1, namely 1 times 1, 2. There's a point on L associated with 2, namely 2 times 1, 2. There's a point on L associated with minus 1 times 1, 2. That is to say that the parameterization suggests a just likeness. So again, what we're seeing is that we're using isomorphism. We're using isomorphism to describe somehow just likeness. That the 1, 2 stays fixed and the t varies shows how this line is somehow like the real line with only the letter t to describe it. Verifying that it's 1-to-1 is routine, especially with the check-in. Verifying that it's onto is routine, again, especially with the check-in. If you want to show that, for example, there is a member of the line y equals 2x that maps to 7, you just say to yourself, well, 7 times 2x, 7 times 1, 2 maps to 7. And then preservation of addition and preservation of scalar multiplication is on the next slide. Whoops. Preservation of preservation of combinations is just as routine. To show that f of a combination is the combination of the f's. To show that f of a combination is the combination of the f's is just the kind of algebra that we've been doing. You bring out the 1, 2's, f applied just simply strips out the 1, 2, and there you are. Okay, so again, the idea here is that these maps, something I expect is new to a person, these maps describe something about the spaces in a precise way, but describe something about the spaces that you've probably already intuited in the second chapter. You said to yourself, well, this is really just like. Yes. So for example, the line y equals 2x is just like the regular real number line in that, for example, 5 times 1, 2 is just like 5, and 12 times 1, 2 is just like 12. Yes, that's right. The definition of isomorphism simply makes all that mathematically precise. Okay, very good. Next time we'll talk about dimension characterizes isomorphism, and so we'll see you for next time. Okay, bye bye.